This is lesson 5 in the thermal physics topic. It is on specific latent heat, which is different to specific heat capacity. Specific latent heat is the energy required to change the state of 1 kilogram of a substance without changing the temperature. This is different to specific heat capacity because specific heat capacity is all about the energy required to change the temperature, but latent heat is about changing state without changing temperature. So to summarize, specific latent heat is all about changing state. Specific heat capacity is all about changing temperature. There are two types of specific latent heat. There is specific latent heat of vaporization, which is changing state between liquids and gases. And there's specific latent heat of fusion, which is changing state between solids and liquids. The equation for specific latent heat is E equals mL. Energy measured in joules equals the mass measured in kilograms times the specific latent heat of either vaporization or of fusion, which is measured in joules per kilogram. This is a worked example of a question that uses the equation. So question is, how much energy is needed to melt 500 grams of ice? Well, first of all, we're going to start off with the equation E equals mL, and the mass that changes state, m, is 500 grams, and so that is 0.5 kilograms. L is the latent heat, and because it's melting ice, we're looking at fusion, not vaporization. We're looking at the fusion value. So L is this top value here, 3.35 times 10 to the power of 5. Putting those into the equation, mass times latent heat of fusion, gives me the energy required to melt it is 1.675 times 10 to the power of 5 joules. Have a big answer there. Please get a pen and paper and calculator now, and try out the rest of these questions. I will show the answers in a moment. Just green pen those and make sure you got your answers right. If you aren't too sure on any questions, just let me know and I can show you how to do them. Now, so far I've spoken about energy being put in to a substance to make it change state. So we're talking about putting energy into ice to make it melt, or putting energy into water to make it evaporate. But actually, if we go, instead of from ice to liquid, or from solid to liquid, if we go from liquid to solid, we actually release energy. If we go from ice to liquid or liquid to water, we need to put energy in. So we need to put energy into ice to make it melt, or we need to put energy into water to make it evaporate. But if water vapor evaporates back to a liquid, it releases energy, releases heat. Same thing with liquid water going into solid ice, solid water which is ice, it releases heat into the environment. This is actually why clouds are warmer than the air around them. Clouds are actually not water vapor, but lots of tiny little liquid water droplets. When the water vapor in the air condenses into those tiny little water droplets, it releases energy as heat. So clouds are hotter than the air around them by quite a few degrees Celsius. We can try this in a question now. How much energy is released when freezing 500 grams of ice? So how much heat energy gets released when you freeze half a kilo of ice? Well, we're going to need the specific latent heat of fusion of ice value. Same thing again, because it's the do with between solids and liquids. And we do the same steps as the first question. E is equal to ml. The mass is half a kilogram. Same latent heat of fusion value. But this time, this is the energy that is released by the water as it freezes, rather than the energy we need to give it to melt, which is what we did first time. How do we calculate latent heat of fusion? Well, you could get an experimental setup like this, where you've got some ice inside a funnel like this. You heat up your ice with a heater, you ensure the temperature stays the same, and you measure the mass that melts, and using the two equations, you can work out the latent heat of fusion. So you use IVT to work out the energy put in, you measure the mass using a mass balance, and you can work out the latent heat of fusion. The equipment you need to use and what you would do to ensure accuracy are given as follows. Pause it if you need to read it. You'd want to use some insulation to make sure that all of your heat energy went into melting the ice rather into the atmosphere as well. Calculating the latent heat of vaporization is a bit more difficult. This time, what you have to do is you have to get some liquid in a little round bottom flask, heat it up until it evaporates. So that is you giving energy to the liquid to evaporate it. And then the gas fills this round flask. What you then get is you then have a condenser attached to that flask. And the gas that has evaporated will spread into the condenser or the tube within the condenser. and the condenser will bring your gas back to a liquid again, and it will collect in the bottom. So what you can do is you can measure the heat energy you give to the liquid by doing IVT again. So you measure the energy given to the liquid. That tells you how much energy you've put in to evaporate the liquid. And then using the condenser, you sort of recondense that gas back into a liquid again, and you can measure the mass of that liquid, and that gives you your M value in the E equals ml equation. So you use this to work out the energy you put in. You are using the collecting flask to recollect the gas back into a liquid to measure it, because you can't really measure the mass of the gas very easily. And once you know E and M, you can then calculate the latent heat of vaporization. The most difficult calculation questions you'll come across in specific latent heat are questions that mix together specific heat capacity and specific latent heat in the same question. Now I've got another video, I'll link it in the description. You can click on that to show you how to do this questions like this. I'm going to show you how to do this exam question. And in this exam question, it's where you put a very hot bit of copper into a beaker, into a copper beaker that's got some water in it. The copper beaker will cool down, but as it cools down, it gives heat energy to the water, heating the water up. But then it keeps on heating the water, it keeps on giving energy to the water, and eventually some of the water will evaporate as steam. And I'm going to show you how to do those questions in the next video. And they can be quite tricky questions. There's quite a lot to do in those. So do watch that to show you how to do it. If you want a bit of extra reading, you can click on this link here. I'll link it in the description as well. And it explains to you the physics behind why we sweat to keep us cool. So there's a lot of physics behind sweating.